Hi, Glass. How's it going? Today we'll cover Chapter 8, and that's conservation of energy. And so using our idea of work, right, where work is, so if you remember from last chapter, work is equal to the line integral of the force dl. And what this says, right, we have the dot product. So what it says is that the work that we do on an object, or the work done by an object, is equal to the force applied in the same direction as the distance that that object moves, right? This tells you how much of that force, it really tells you almost how much of that force is being used to move the object, to do work on the object, to physically manifest something, right? Now, using this idea of work, we'll start solving these kinematic problems using work instead of the kinematic equations. And this simplifies our lives tremendously, which we'll see why in a minute, right? And now work is a form of energy, right? Now, it's really interesting. What is energy exactly, right? And there's actually not a very good definition of what energy is. So if you think of a meter is very well defined, right? It's a unit of length. We live in this environment that has space, and it's defined as a unit of length, right? It's from here to here, from point A to point B. But energy, it's an abstraction. We don't know exactly, we don't have a good mental picture of what it is exactly. And actually, Richard Feynman said, mentioned it in the past that energy is not well defined. It's known as an abstraction, like I just said. And what he means by this is that it's more like a number, right? We can measure this quantity. We made it up, right? We made up what this quantity is. Force times the length, right? We made up this quantity, and it seems to work out very well for solving these problems, right? There's no definitive unit of energy, like there's no single unit that we can break it down into. So it's this abstract quantity that somehow we could use to study systems, right? And we'll go into it now. So now the way we'll use energy will depend on the force. Now there's two types of forces. There's a conservative force and non-conservative force. And non-conservative. Right? And the difference between these two forces is that one is the non-conservative force depends on the path that you travel, while the conservative force does not. What do I mean by that? Okay, so let's say we have this graph, right? X and Y, and imagine that we're moving a ball upwards to here. Moving the ball upwards to here, right? And this is a length of h, right? The amount of work I have to do, ignoring all other forces besides gravity, right? The amount of work that I have to do to move this ball upwards to this height, right, is just, you know, if gravity, if G is downwards like this, right, it's just the force times the length. So the work in this case is equal to the force mg times the length h, right? Now let's consider a second scenario. Let's take that ball, instead of moving it straight up, we move it upwards, but we also move it along the x path. Let's say something like this. Now how much work do we do? Now it's the same thing that G is totally downwards, right? No matter where I move this ball, the direction of G will never change in the environment that we know here on Earth, right? It's always downwards towards the center of the Earth. Because of this, right, the work that we do moving it from here to here is the same. mgh. Right? And if we look at it, this if this is YA and YB, this is YB, this is YA prime, and this is YB prime, right? If we look at this, it doesn't, the work that we do on the gravitational force, or due to the gravitational force, or the work done by the gravitational force as this ball drops back down, it doesn't depend on the path. All that it matters is the endpoints, right? All that matters is this quantity. Okay, so all that matters is the endpoints, where the height that we begin at and the height that we end at. And even the x endpoints don't matter. All we care about is how far we move in this direction, right? Vertically. In fact, it doesn't even matter if we move up or down, right? If we go like this and down and we end up at the same point, the work that is done on the ball by us to lift it up to a certain height is still the same, right? Because whatever I move up over here, I move it up to this height, I do a certain amount of work. When it drops back down, I gain the ball gains that energy back, right? So whatever work I put in, by lifting it to a higher elevation, I gain it back when it drops, right? And it doesn't matter about the path, it just matters about the height, right? Now, a non-conservative force is something that's path dependent. So can you think of a force that really depends on the path? It always depends on the path. What force that it just depends on how the direction that you move in. The prime example would be friction, right? Friction just is path dependent, right? The amount of work I move the ball over here depends on the path I take, right? If this is L, then it would be the force of friction times L. Right? And if I move along, if I change the path, I increase it and I go like this, right? Everywhere you move it, it's resisting the motion, so it's path dependent, right? And in this case, we would have to do calculate the distance that it travels, right? You know, if it travels a distance L again, we'll use the same number. It would just be the force of friction times L, right? So this is a non-conservative force, right? And we break this up into two types of forces because this will help us be able to calculate the kinematics of objects when they're under these two different forces, right? So the real advantage of using conservative forces is that it doesn't matter what path you travel on. I just care about the beginning and end points, right? And I could calculate everything about this endpoint if you give me the beginning, or I could calculate things about this endpoint if you just give me the final and initial starting points, right? Now, that was not the case with the kinematic equations, right? We cared about how much time it was in the air, and we could figure out the velocity, the final velocity from how much time we spent traveling through the air, through its motion, and we were more concerned about what happened during the trajectory of an object. Here, all we care about is snapshots at different times, and we can figure out what's going on with this, with the object in question. Now let's focus on the conservative forces right now, because they're much more simpler than the non-conservative. Okay. So the main conservative forces are two that we'll really deal with. It's gravitational, the gravitational potential energy. Well, I'm sorry, not potential. We'll get to that in a second. And the spring force. Now I introduced the I'll just leave it like this. I introduced springs last chapter, right? I said that a spring, right, the force that a spring exerts depends on its equilibrium position when it's just standing there, when it's just when there's nothing applied on it, when it's just in equilibrium, and it's dependent on how far away from the equilibrium it goes, right? And now this is a conservative force, because this force is always in this direction, right? It never changes. So we don't care about how much it moves up and down. We just care about how much it moves in and out, right? And it's path independent. It doesn't matter if it starts from here and then it moves around and it ends up back at equilibrium. We'll still have the same amount of work done in the system, right? Now, with these systems, we introduce a new terminology. This is called potential energy. Now, I introduced kinetic energy last time, right? Now, kinetic energy was the amount of work that a moving object can do on something because it's moving, right? If I throw a ball at an object, or let's say at some bowling, some pins, you know, I throw a ball at the pins in a carnival ride, right? The motion of the object will exert a force on those pins, right? And then the velocity will change of the ball, and the pins will pick up a certain velocity, and the ball does work on those pins. It knocks them down, right? Or moves them around. It does work. And that's what kinetic energy is associated with, right? The amount of work that a moving object can do on another object, right? Potential energy is a little bit different. This is the amount of work that can be done in a system based on its configuration, right? So let's say on Earth, right? We're on Earth, right? And we're in an airplane, or we're skydiving, right? That's my little guy trying to draw an airplane. Let's just say we're going skydiving, and he opens up his parachute, right? And we take a snapshot at this point, right? Now, you know what? Actually, a parachute is a bad idea because he is not picking up any velocity. Let's say he just jumps out of the plane, right? And right at the moment he jumps out of the plane, he has no velocity in the y direction, right? Let's say he jumps out of a helicopter submarine. It's not moving relative to us on the ground. He has no kinetic energy, right? But he has the potential to gain kinetic energy, right? The second he jumps out of the airplane, right, he still has basically no kinetic energy, right? But because that he's in the air, and due to the gravitational field, he'll experience an acceleration and a force. And he has the potential to gain energy, or to gain kinetic energy, I should really say, right? So at this moment, this configuration of the skydiver and the Earth, there's a certain energy associated with that, right? He has the ability to gain energy. Or if I compress a spring, right? Let's say if I compress the spring, and here's the equilibrium position, and I hold the spring here, this has the potential to give kinetic energy to whatever object is on that spring, right? Because as soon as I release it, it'll give it kinetic energy, right? There's a certain amount of energy associated with this configuration, right? And this is what we call potential energy. It's right there in the words, potential energy. It has the potential to gain, to have work done on whatever object in question, right? There's no work being done right now, but but there's the potential of that work being done, right? You know, if we just release it, you know, it'll do work on the system. So that's potential energy. Now, okay, so with potential energy of a conservative force, what we really are concerned with is not exactly the potential energy at any given point, but the change in potential energy. That's all we really care about, is the change in potential energy. And let me show you. So the change in potential energy right? Over here from 1 to 2, right? And the way we define potential energy is we use this term U. That's what we use to define, to represent potential energy. So U1 at this point, right? Let's say we start at this point and then somehow we move it to this point. So U1, the potential energy would be mg. Now, how do we define the height? Do we define it from the center of the earth, from the floor that we're standing on, from sea level? How do we define the height that it's at, right? And for right now, we could just use a relative measurement. So let's say that we define the 0 point as this, sea level, let's say, right? So we have this as y1, right? So this is mgh y1, and then over here, mu2 is equal mg y2, right? And the work done by gravity, right? Because we're doing work, gravity's doing work to move it down here, right? Where it's giving it energy as it's falling down from this height to this height, right? The work done by gravity is equal to the change in the potential energy, right? It makes perfect sense, right? Potential energy is just the work, the potential for that force to do work on a system, in this case a ball. And if it drops from this height to this height, it loses potential energy. So it does work on this ball when it falls down here, right? And so then we get this equation. Y1 is equal to Y2. And this is equal. So right now, if you look at it, right, this would be negative, right? Because Y2 is smaller than Y1. So what we say is that this is equal to the negative work done by gravity, right? Because the gravity gives energy to the ball over here. So it's a positive, it's a positive sign. The work done on the ball by gravity is positive. But it would be a negative change in potential energy because it's taking it from somewhere. And this lets me introduce another important caveat to this chapter and the previous chapter. Energy cannot be created or destroyed. It has to go somewhere. You have to account for this quantity that we're measuring, this work that we're measuring, this abstract quantity of work, the force times the distance that the object moves. It has to be accounted for. It's like an accounting system, right? But we can account for this quantity that we call energy, and it always adds up and subtracts. It goes somewhere, right? And this will lead us to conservation of energy. Well, this is conservation of energy, right? Where energy cannot be created or destroyed, it has to go somewhere. So, according to our understanding of the universe was created with some amount of energy, and it hasn't changed. It always goes somewhere, right? Now, this wasn't always the case. We really solved this in the 1800s, and the reason for this was basically due to friction, right? When you push an object, what happens due to friction? Where does that energy go? and they didn't understand where it goes. But what actually happens is that it goes into heat. So we didn't understand that heat was a form of energy. And the way we actually describe heat is it's the kinetic energy of the molecules in your body. So heat is a direct measurement of how fast the atoms are moving in an object, or in our case, our body, like how hot we are. It depends on literally how fast our molecules are moving around. And based on this, we say that the heat, the energy that's lost due to friction goes into heat, and it goes into the kinetic energy of these molecules. So it's accounted for. And if you notice, any friction creates heat. Rub your hands together, you instantly feel that it's getting warmer. That's the kinetic energy, right? That's the transfer of the work I do on my hands to heat. And all the energy is accounted for, right? So it's energy is really like almost like an accounting system, right? Now, so for this, if we're letting the ball drop, the work done by gravity is equal to the negative of the change in potential energy, right? We do positive work on the ball by gravity, and it's equal, and it comes from its loss in potential energy, or the loss in the energy associated with this configuration. Now, let's say the other way. Let's say we go backwards now. Instead, we go in this direction. Now, how does it look? So, the change in potential energy in this case would be y1, because that's our final position, right? Minus its initial potential energy, y2. And, or I'm sorry, not y2. This should be, let me write it out, mg1, right? And this is equal to the work exerted on the object, right? I have to lift this object up. Or if this is a backpacker carrying a hiker carrying a backpack up a hill, this is the work exerted on the object. So I'm transferring, I'm putting work into this configuration with a gravitational field, right? And it's equal to the change in potential energy in this case is equal to the work I put in. How much energy do I put in? That's how much energy goes into the configuration of the system, right? And these are pretty simple concepts, right? And because they're so simple, they're very, very powerful to solve these problems, right? Now, let's consider a situation, right? A good situation to look at is a roller coaster, because a roller coaster uses changes in potential energy to give the riders kinetic energy, and the wheels, they minimize friction due to how well the carts are built, right? So let's say if we start at a certain height and we raise up to over here, and then we drop down, right? We have these two positions, right? And then this is 10 meters, and this is 15 meters. Right? So the potential energy at point one, the potential energy at point 1 is equal to mg times the height. Now, in this case, right, let's say this is the lowest point that we go in the roller coaster, right? And then it goes back up, right? At point 3 is the lowest point. There's no reason to consider the ground 0 in this case. It just adds complexity, unnecessary complexity, because all we care about is the change in potential energy. So for us, if this is the low point that we go on this roller coaster, or a little roller coaster, some people, one person on it, if this is the low point, all we care about is the difference. So we could choose our 0. So in this case, let's choose this to be 0, right? So now the potential energy of 1 is just here from 3 to 1 is just 15 mg times 15, right? And let's say the mass of this cart is 1,000 kilograms, right? So this would equal 1,000 times g times 15, right? And then this will equal to 1,500,000 joules. Or, I'm sorry, yeah, that's fine. So the potential energy associated with this height is 150,000 joules, right? Yeah. Now, in the book, I'm working off of example 8.1. The 0 point that they take in the book is over here. They take this as the 0 point, but it doesn't actually matter, right? In this case, the work done, the amount of potential energy compared to 3 is 1,500, right? Joules. If we take this to be 0, let's say, let me use a different color marker. Let's say if I take this to be 0, and then I want to calculate the potential energy of 3, it would be mg minus 15, because this is lower than what we take to be 0, minus 15, and this comes out to be minus 150,000 joules. So this has a lower potential energy than that, right? So it doesn't matter what you take as your reference point, really, as long as you're consistent. So we'll use that as our reference point. Now, U2, the potential energy at 2, is equal to mg times 25, right? 15 plus 10, right? And then we could do the math from this. 9.8 times 2.5 times 10 to the 4th, and we could calculate that, right? If we round this up to 10, it would just be 2.5 to the 5th power, right? 250,000 joules. Right? And that's how we deal with this, right? Now, and then we'll relate this to the kinetic energy in just a minute. So in general, the gravitational potential energy, the change in gravitational potential energy is equal to the negative work done by gravity, right? And this is equal to the force of gravity times dotted with dl. And in general, this holds true for any conservative force. The change in potential energy is equal to the negative work done by that force. So this is the general rule. So now let's consider a spring. Let's calculate the potential energy of a spring, right? This is just equal to mgy, right? And how did we get there? So let's actually calculate the formula for it, right? And so it's the force times the distance that you travel, right? Because it's a conservative force, it's only in one direction. So we do this, F dy. The work done on something is just F dy. And for us, it would just be mg times dy. And this integral, I'm sorry, this should be L. And because the force is only in the y direction in the problems that we deal with, or vertical, this dot product becomes this, right? It's just only in the y direction, this force. Or just in one direction, right? And then this just becomes mgy, right? That's how we calculate this. And then we can relate this to the work done. We can relate this to the potential energy by the work done on the system, right? Now for a spring, or I should really say elastic U, because it doesn't matter if it's a spring or a rubber band, it still works basically the same way. As long as you don't deform it too much, it depends on the the force is linearly proportional to the distance from equilibrium. So elastic U, right? And in this case, we know that U is equal to negative work, which is equal, I'm sorry, this should have a minus sign in front of it. And this is equal to the force of a spring times dl. So what is a spring? The force of a spring is equal to kx right, is negative kx, I should say. Negative kx where x is the distance from equilibrium, right? So let me just draw it out. So this is the equilibrium position. If I don't push it down, let's say I compress it by pushing my hand on it. or my foot. I push it in, and this distance is x. This distance is x. So now we have this. Let's plug it in. Kx times dl. Right, this is all in one direction. The negative signs cancel out, and then we get, let's say this is position 1 and this is position 2. Then we get x dx, right? So let's take the integral for x dx, and u of a spring is just equal to 1/2 kx squared, and then you go from this position to this position. So it's equal, so then at position 1, there's no force, right? So it's 0, or I'm sorry, at position 2, it would be, let's call that, we're calling that x, right? X over here is a variable, and then we just call this distance x, just as a very general distance, right? So just be careful with this, right? This is a variable. A lot of people, what they do for here is they put a prime. They put a prime x, and then the integral is from 0 to x. Let's do it this way. Right? And we plug it in, and we end up with this, right? Minus 0. And this gives us the definition of for a spring. The change in potential energy, or its potential energy, we should really say its potential energy is this. For a spring or an elastic force, it doesn't matter, because the spring is just the manifestation of the material's elasticity. So now we calculated the potential energy from the force. Now, a lot of times, so the force is a vector, right? Is potential energy a vector? No. Work is not a vector. Energy is not a vector. Why? Because it is scalar product, right? The scalar product converts two vectors into a scalar quantity. That's why it's called a scalar product or a dot product, right? Where you multiply the components together, right? So this is a scalar product. So it's easier to deal with the energy because it's a scalar product. All we care about is the beginning and the end. We don't care about each individual component. Makes our life simple. So it's easier to start with the potential energy and to figure out the forces from the potential energy. So how do we do that? So the force is given by that dot product integral, right? So we have this, right, generally. Now, let's get back the force from this, right? Now, how can we get back the force from this? Well, if we do an integral, if we do a derivative, it's just the opposite of an integral. So let's do a derivative on each side. And that will give us back the force, right? We have a derivative of an integral. They cancel, they negate each other. And then you have the c, some constant, right? So here we'll just have u dx. And then these two cancel out, so we're left with the force. And then this is 0, right? Because it's just the derivative of a constant. And then we're left with this equation. So the force is just equal, in this problem, it is equal to the change in potential energy in the x direction. So the force in the x direction is equal to the potential energy, the change in potential energy in that direction, right? Now, if we apply this to all 3 dimensions, right, what we get is the general case. So we just apply this to each, remember the force has direction, we apply this equation to each coordinate, and to each coordinate system, or each direction, each degree of freedom, I should really say. Sorry, I couldn't think of the word. So when we do this, the force vector, which can depend on all 3 variables, translational variables, right? This is equal to the negative of the work done, the derivative of the work done in the x direction. That will give me the force in the x direction, plus the derivative in the y direction, and then plus the derivative in the z direction. And we get this. So really what we're doing is we're taking a scalar and we're using this process of taking the derivative in the direction that we want to look at, and that will give us the force in that direction. So we're taking a scalar product with a scalar and we're turning it into a vector. Now, if you've learned this, if you've taken enough calculus, I'm not sure whether they teach this in Calc 2 or 3. I think it's in 3, but because this is vector calculus. This process is called the gradient, and we simplify it. So we say that the force is equal to the negative gradient of the potential energy. And here, the gradient is just this process of taking the derivative in the x direction, and that's the component of the force in that direction. The derivative in the y direction is the force in the y direction, and then so forth for z. And so we can figure out the forces from the potential energy. Right? And it's quite interesting because it kind of looks like we're getting something for nothing, right? Because the force has direction, the scalar product doesn't, and somehow magically we get 3 different components by this process. And this is allowed because it's a conservative force, because it doesn't depend on the path, it depends on the endpoints, and this is why this works. Right?